we will tell you a bit about the now old the Virtual Brain project and its new developments and new deployments into eBrains. This is work in close collaboration with other groups, especially Petra's group in Charité and Victor Rirsa's group in INS. So we are the technical geeks putting the scientists' work into practice. I said old TVB because this year, some of you might know, TVB makes 10 years as a software project. And that's a lot in the software world, and we are proud of it. On the current agenda, we talk a bit about the architecture at the beginning, and then we focus on new modules that exist in TVB, in particular integration with ontologies, BIDS integration, inversion, and also deployments into eBrains, which I think are of special interest today, as the workshop is about eBrains Health. And here we have two of them to focus with technical details. One is in integration, the deployment that Jill and Dionysios showed you earlier with the multi-scale, and the other one is about the pre-processing pipeline developed by Charité, which has been deployed in eBrains also. And with this said, let's dig into the architecture of TVB. But first on the principles, what we like a lot is the open science principles, and we try to incorporate them closely into our work. In particular, we chose open source direction for most of the modules in the Virtual Brain world. And the license that we use is GPL version 3. This means it's open, the code is visible, and everything using this code needs to preserve the license. It cannot be closed further. We are focusing on covering most of the architectural operating systems, Linux, Mac, Windows. And we are trying to accommodate users that are fond of the console interface as well as a web interface with buttons and input fields. And also what we found as most fitting for the scientist, it's a mixed world where you have access to graphical components that are easy to manipulate, but also you can dig into the code through some commands and make adjustment yourselves, because as you probably know better than me, research is never fixed. You cannot be put into a few buttons. You cannot put your thoughts on a few buttons and input fields, so you need more. And here Jupyter Lab is quite a useful tool, and we have a few widgets for it as well. So this is the world of TVB in principles. In technical details, the world of TVB modules is mainly around Python, Python 3, and we have the classical NumPy, SciPy modules, but we communicate, we display results with WebGL, for example, in D3 over HTML5. We store results in a relational database, Postgres usually, in order to have indexing and fast access. We also have accelerations, which are done with Numba or C code. And on top of these programming languages, we have other tools that are useful, like Jira and Confluence for tasks management and documentation. We use intensively Git and GitHub in particular for publishing the code. And we package this code further with tools like PyInstaller. And then we have packages available for direct usage with as an executable, or package it for PyPy, which is the common Python word packages not manager, repository. We have compatibility with Docker for most of the deployments, Docker or Singularity, and these are orchestrated further with Docker Swarm or OpenShift. In some parts, we even use a workflow engine like Pegasus, but we have directions of going towards CWL, which is the new eBrain's used workflow language. At the very core of TVB, we have 4 packages, 2 of them more important than others. The ones in red are the important one. These are called library and framework. The library holds the mathematics, the simulator, which is doing, as you probably know, large scale resolution simulations in the virtual brain, and the framework is holding the web interface. They use at the bottom 2 smaller modules, one named TVB data and one TVB geodesic distance. I think the names are quite explanatory. They hold demo data for TVB, and the other one is computing distances on the surface. And these 4 modules, this simple part at the core is allowing to have 2 types of users. One is the graphical user that will need to go through the web interface, so through the framework, and one is the script user that can go either to the Python library of the framework and use the Python API in there, or directly to the simulator. And if we zoom this out, we have now the 4 packages in the red box here. I hope you recognize the name. This is TVB framework, library, GDist, and data. They are packed into what we called a TVB distribution. This is a self-contained package with Python, as well as all the third-party libraries, plus our core modules. And we have a lot of modules around this world. One important module that you heard a lot about today is the multi-scale module here in green. This multi-scale module, it's again a Python module available on GitHub. It's relying on TVB library and extending it in order to have co-simulations done. So it adds the co-simulator class and multiple model classes, extending the core classes of TVB simulator. And similarly, there is another module called TVB epilepsy that's focusing on the epileptic pathology and doing fitting over SEEG signals empirically recorded from patients, and then using the TVB core library in order to make this, to adjust the simulation to match the patient's signals. In principle, this schema, what it shows that the TVB world works between the measured patient data on the left from T1 diffusion weighted images through a reconstruction pipeline, computes some structural representation of a patient, in particular, and most importantly, a structural large-scale connectivity. It simulates or it does data fitting in order to produce a virtual representation of that brain. And this virtual representation of the brain will be like a digital twin, if you like, where certain operations can be executed in this world, virtual world. And one more principle about our architecture is data. We consider that data is a critical resource that we have to manipulate within TVB. And thus, we adopted something that is called data-centered architecture, meaning that at the very center of our classes, we consider data organization. And thus, we have data types, a set of Python classes that are in memory, modeling how the data is representing. And we have one class for the large-scale connectivity, one class for the surface, for time series, and so forth. And by having data in the center, we further organize operations just around them, like the simulator. The simulator is a satellite node that is taking as input a connectivity, and it's producing as output a time series in the simplistic manner. An analyzer will take as input one time series and compute as output a Fourier spectrum data. And this one can be later on stored, visualized, or exported into some formats. But by doing this by implementing this architecture, we separate the analyzers and the simulator. They don't need to depend one or the other. They just need to speak the same language, and the language is the language of our data types. And with this architecture in mind, we will see next one example of how this was extended by adding a new adapter called TVB Zebra. And probably you heard about Zebra. Zebra is a Python client mainly developed by the Human Brain project, especially for accessing eBrain's human brain atlases. It's working with brain atlas frameworks in general, the ones that integrate multiple brain parcellations, and they connect these parcellations with regional data features. I was citing now from their official documentation of Zebra. And in TVB, we just added one of those satellite nodes in a Zebra creator that will appear in the graphical web interface of TVB as highlighted here, a Zebra connectivity. It allows us to import connectivities from eBrain's knowledge graph using this Zebra library. And after clicking on it, we will be taken to a page that is giving us few options. I don't think they are quite difficult to understand. We can choose the atlas, the parcellation, what subject we need extracted. But one input field is, it's a bit odd. It's the eBrain's token, the first input field. This one will appear enabled in the installations that are local. For communicating with the eBrain's knowledge graph, in some parts of it, one needs to have an access token. And we need one which is valid for eBrains. And for the local installations, you could get one if you log in first on eBrains Lab and you open a new notebook and write something like collab authentication get token. And then you copy paste that into the TVB web interface. This is for the local installations. In the installations that we have on eBrain's OpenShift with TVB, this token doesn't need to be manually copied. It will exist in session because TVB web installations are connected with eBrain's authentication key clock and does have that already. Once we launch an operation with Zebra Creator, on the current project in TVB web interface, we will have a new row like here on the top, Zebra Connectivity Creator launched by user administrator at a certain time. It took about a minute. And it produced some results if executed with success. Technically, what's happening is that we have TVB framework, this Python module, that's communicating through Python API with Zebra. And this one is communicating further with the eBrain's knowledge graph through its query language and taking back some data, which is later on presented to the TVB framework. And here in TVB framework, we have a new adapter that's wrapping the data received by Zebra, these arrays of adjacent matrices for connectivity, and translating it into connectivity data type of TVB in that pool of data types that TVB stores inside, and then it can be used later on by other operations like any normal data type in the virtual brain. This architecture has a few soft spots. One being a chain. It means that any bug or problem that exists in the communication of Zebra with the knowledge graph will reflect into TVB. And yes, we have now one of such problems that Zebra cannot communicate with the latest knowledge graph updates, and thus importing it into TVB large-scale connectivity doesn't work for the moment. But it should be fixed soon. So this is a feature for future releases of TVB. More deeper into the architecture of TVB, what happens when an operation is executed? We have the framework or the web interface where the operation is submitted, but the actual operation is just stored and scheduled for launch by this front-end part. Later on, a scheduler will come and actually launch the operations, which will read the inputs from storage or from the database index, and then execute the operation and write data back in chunks. This scheduling and launching separations allows us to deploy TVB in environments that have powerful backends, like HPCs, and thus the execution will happen detached from the actual click on the button in the web interface. As a result, in the web interface, we could see one Zebra result here, which was produced last month when Zebra and Knowledge Graph were able to communicate correctly for a subject named 042, and we extracted the large-scale connectivity and and 5 functional connectivities that are displayed in a tree-like manner here. I see the chat. Should I open it? Are there questions that needs to be addressed now? I would have 1 minute before going into the next module.
Yes, Leah, there's actually the question, when will be the release of these news and when is it accessible?
Good question. Paula, would you like me to answer now, or should I leave the surprise to you? Because there is a slide for that.
You can say it now. Whenever it's convenient, but maybe if I'm not here when you say it, then disappointed. If you could just anticipate.
Okay, then I would anticipate. So the next release is scheduled to happen this week, so in a day or two. But with the Zebra problem that I just mentioned, this feature might not be enabled. It's not up to us in particular. If there is somebody from Zebra or the eBrain's knowledge graph here, they might have a comment on that. I'm not sure.
And you may be able to recruit us as beta testers. I'm not expecting you guys to roll out a perfect environment. It's very complicated, very high end. But I'm kind of very happy to roll out if you need. I'm just mentioning it, so I'm leaving it up to you. Thank you so much.
Okay. Let's go into another new module of TVB, which is called TVB BIDS. This is addressing the, I think now very well-known format BIDS that's helping us put in order data when there is stored in a folder. And for TVB, what it means, TVB BIDS is presented as a new client tool to be used like a desktop client application. Imagine the scenario where you have a bits data set in a single folder on your local drive. TVB module can be put nearby to provide a mechanism that monitors this folder for addition, for example, from another software or for manual addition to it. But any file added to that folder can trigger an automatic import, and this bits monitor, TVB bits monitor, will push the new data to TVB web installation that is under your control, and this data will be then arranged or wrapped into TVB data types that are visible in the graphical interface of TVB and can be used later on directly there. As blocks, we have the data set bits local, we have a monitoring daemon, and then we have the graphical interface of TVB, which can be on eBrains, on the local machine, or it can be in an institute server in the same local network. And as packages, we can recognize here TVB framework in the web part, and locally for the monitoring daemon, which makes the TVB bits, we have a new module, TVB bits monitor, which is incorporating a TVB REST client that's communicating with the framework. As an important detail here, this module was developed in collaboration with a student named Akash Upadhyay in Google Summer of Code this year. And Paula, my colleague, was his mentor, and INCF, the organization, the umbrella organization that that orchestrated the collaboration through them to Google. This is quite a success for us, I would say. It's not the first year when TVB participates in Google Summer of Code. I say a success not for the code that is produced and not so much for the fact that it's a new model, but by the fact that external contributors that are not part of TVB core can contribute to this open source project, which is TVB, and add new modules, fix bugs, report bugs, add critiques, or other improvements. Moving forward, there is another change in TVB around the Brain Connectivity Toolbox. Brain Connectivity Toolbox is not something that TVB owns. It's a toolbox developed by Olaf Sporns, I think in Canada. It's older than TVB as software. It contains many functions that are computing some metrics based on graphs, and graphs in particular brain connectivities, structural connectivities. We take from TVB the weights metrics of a connectivity that is representing how regions are, with what weight regions within the brain are connected. And these connectivities are then analyzed by the Brain Connectivity Toolbox. And this is, again, a satellite box around the data types in TVB for us. And there are algorithms from, I don't know, distance algorithms in Brain Connectivity Toolbox, density algorithms, clustering algorithms. And later on, after we run one of these analyzers, we get a vector, which is giving us a number for each of the regions in the brain, and then we can plot the results like here. So this is not new. Integration of Brain Connectivity Toolbox was from the very first versions of TVB available. What's new, and I think good news for us, is that Brain Connectivity Toolbox released a Python module that is rewriting the original functions which were MATLAB. And for integrating MATLAB functions within TVB, it was a bit tedious because the user had to have the runtime of the MATLAB installed locally. And then we had to link to it in the settings of TVB. And depending on the version of the MATLAB and the operating system, that was not always the same, and sometimes quite tedious. So now we replaced the MATLAB adapter with a Python adapter. And what we did was just changed a bit the adapter inside, nothing around in TVB, but the data center architecture functioned quite well in this case also. And with this, I have ended my part of the slides. I would like to hand it over to my colleague Paula. But before, maybe there is a minute to answer questions if there are some. No? Okay, then. Paula, would you like to take over? Should we?
Yes. I can try to share my screen. Maybe that's better.
If I stop sharing my screen.
Okay. I think you can see it now.
Yes.
Okay, so hello everyone from my side as well. I will start by shortly mentioning a new module that will be added soon to the TVB ecosystem. We call it TVB inversion. And as its name already suggests, it is meant to solve the inverse problem. With only TVB, we can solve the forward problem, where we start from mathematically modeling a brain, then we can compute simulated time series for it. With an addition like the TVB inversion module, we can start from empirical time series, perform fitting, and determine the actual model parameters that should be used to reproduce that empirical data. A lot of effort has been put into solving this inverse problem. Thus, there are many publications around this topic, and the solutions are based on different algorithms like HMC, machine learning, deep learning, and so on. In this particular module, the solution is based on SBI Toolbox, which comes from simulation-based inference. The purpose of this model is to help users which are new to the topic to start using such inference tools. Thus, we are striving to provide a simple API using TVB principles as much as possible. So users which are already familiar with TVB, the command line interface can quickly onboard and use this module. The API consists of 5 steps for now. The user has to configure a TVB simulator first. This will be used later by the SBI Toolbox. Then the next step is for the user to define priors as a list of simulator parameters together with distributions to sample from. Then it will remain to sample those priors, train the network, and finally compute the posterior estimation. Some steps are more extensive than the others. For example, the priors computation part, there is where a large number of simulations are being launched. And for that purpose, TVB inversion will provide means to parallelize or remotely launch simulations. One way is to remotely launch the simulation on an HPC, and the simulations in the prior step will run on the HPC, then the results are copied back, and the rest of the steps for the training and the posterior computation can run locally on any machine. We also have a collab on eBrains with basic documentation on the installation part and the usage of this module, but this is currently private. We can offer you access if you're interested, just ask for it. And the repo is currently under the procedure to being made publicly released as part of the Virtual Brain Cloud project very soon, I would assume, in the next weeks. Okay, and with this, I will move on to the next chapter of this presentation, which refers to the deployments we have now on the eBrains platform. Different flavors of TVB are available in eBrains, and depending on the user's preference, they can choose whether they want to work with the command line API or with the GUI. Within the eBrains lab, we already have the TVB library available in the default kernel, so the users can directly create a new notebook and import TVB without needing to perform an extra installation. We keep the versions up to date there. We deploy TVB library as a Spark package to eBrains, that being the deployment procedure agreed by the eBrains technical coordination team. Regarding the GUI, the GUI of TVB can be found at this URL, tvb.apps.hbp.eu. It will open a common landing page for 3 versions of TVB. The first 2 are stable versions, but the difference is that one is hosted at CSCS while the other is hosted at Jülich. And the third one is a prototype version of TVB featuring a new page that allows users to start up the pre-processing pipeline. And I will show a bit of that in a few minutes as well. If you choose the first option, you can click this and it will take you to one of the following links, either the virtualbrain.apps.hbp.eu, which is the installation on CSCS, or the second one, which is the installation at Jülich. So once you choose one of the installation, you will be redirected to this page where TVB requests your eBrains credentials in order to grant you access to the application. So any eBrains users can access it, and we achieve this authentication mechanism by integrated with the eBrains Keycloak system. And once you are granted access, you can browse the TVB pages and start experimenting with its features. One more thing that would be important to mention here is the data and how data is structured in TVB. The data you import in TVB is organized into projects, and users can see all their projects on this project list page. These projects are shareable, and it is the project owner's responsibility to decide whether other users are allowed to access a project or not. This sharing operation can be done in the page called Project Properties. On the right side, the owner of the project can see which users already have permissions to access this particular project, but also has the permissions to edit this accessibility. This sharing operation can be done, this sharing operation can be done only by the owner. So all users have access to this page, but this part will be read-only unless you are the owner of that page. On the left side, the users can edit the name and description of the project, but there are two new flags that will be added in the next release of TVB, which will happen this week. And one of them is a flag that allows the user to disable imports for the current project. And then the second one is a field that allows the owner of the project to restrict the size of operations that can be launched within the project. These are somehow necessary in the context of centralized installations of TVB, so the owner can have a bit more fine-grained access to restrictions for his project. There is a special project called Default Project that comes with TVB, and this one contains demo data intended for educational purposes to offer users a starting point for learning TVB, and this one is visible to all users that access TVB. All data within these projects can be viewed by any eBrains user that logs into this TVB installation and so on. And with this idea in mind, we discourage users to import data that might be sensitive into the default project that's available on eBrains. And for that purpose, together with the next release of TVB, we will be restricting the imports on the default project to make sure users won't add sensitive data there even by mistake by using this particular flag. Behind the scenes, these web GUI installations of TVB are deployed on the OpenShift platform hosted by eBrains. OpenShift is a container orchestrator similar to Kubernetes. It allows deployment via Docker images, and a setup page for TVB can look like this. You can have multiple Docker images. For example, here we can see one for our Postgres database and one for the actual application, and they interact with each other. It's a nice UI for developers because it offers easy access to configurations and scaling options. And then the third installation that we have on the common landing page with the pipeline processing page can be found. The pipeline processing page can be found as a sub-option into the connectivity category. And just quickly before going into the configuration part, for who is not familiar with what a pre-processing pipeline is, neuroscience data comes in form of MRI scans, as Leah shown before. These scans are not directly compatible with TVB, and they have to go through an image processing pipeline where connectums can be extracted out of MRI together with some 3D surfaces and so on. And those resulting files can be used within TVB. And such a pipeline is installed at CSCS. Users can interact with it from the eBrains lab in a scripting manner. But we have also been developing an entry point from the TVB GUI for accessing that pipeline. And the setup page looks like this. the user has to first upload the data in this field. Then multiple fields are to be filled in for the user to fine-tune the parameters of the steps involved in the pipeline, like matrix or free surfer and so on. The pipeline is made bits compatible, and therefore the raw data has to come in a bits format. On this page, we also validate that the data set is correct before sending it to the pipeline. And in order to achieve this, we have integrated the official bits validator tool. And at upload time, different messages are displayed to inform the users about the process. After the validation happens, in case there are errors or warnings, TVB displays them below the upload field. The errors are displayed in red and the warnings in yellow. Then the next step for the user is to address these issues and to fix the bits dataset manually, and then retry the upload afterwards. Again, if we look behind the scenes, the architecture would look something like this. The GUI configuration page is used to upload the data and prepare the configuration. The data is then stored inside the TVB internal storage. The next step for TVB is to connect to Unicore to set up a communication channel with HPC. And via Unicore, we can schedule the pipeline job and stage in the raw data at the HPC site. Once the job has finished executing, the results are staged out from the CSCS to the TVB storage, and then we can make them visible in the TVB web GUI. If the pre-processing pipeline has finished successfully, the results are automatically imported in TVB and shown in the GUI, but in case there are errors during the pre-processing, we stage out the logs and display them in the TVB web GUI so users could analyze them and understand what went wrong, maybe fix the configurations or adapt the data or something related to that. Such an architecture is can be used in other use cases as well, not only for the pipeline. And a more generic representation can be on this slide where we have the TVB web GUI that's deployed on OpenShift in the center, and it communicates with a backend HPC where besides the pipeline, large simulations or parameter space exploration could be remotely executed and then staged back into TVB for visualization. This is a similar representation of the diagram that we've seen previously. So we went through the base TVB deployments, both in eBrains Lab and the OpenShift. There is one more deployment that we maintain in eBrains, and this one refers to the TVB multiscale module, which proposes an extension of the base TVB to co-simulation use cases. You will find this familiar if you participated in the previous session, as it has been already shown by Dennis, but I will just say a few things about the deployment. The installation is available at the link on the top of the page. The deployment is done on OpenShift as well in the form of a Jupyter Lab environment that comes with all the dependencies installed. It is separate from the eBrains lab because we still need control over the dependencies versions. Plus, there are some compilation steps that are done at runtime. Each user gets access to these two folders, contributed notebooks and TVB multiscale examples. The contributed notebooks folder is empty at first, but it can be considered a personal space for experiments with TVB multiscale. Users can add their own notebooks in there because it is not shared with others. So it's a personal volume and it is persisted over time. So you will not use your work if you store the notebooks there. The second folder is the one that contains notebooks with examples from the TVB multiscale repo. This one can change at each release. So new notebooks that are added here will not be persisted over time. Of course, any eBrains users can access this installation and more information can be found within the notebooks with examples. This has already been presented by Dennis. Regarding TVB future, as Leah already mentioned, we have a release planned for the next 2 days for TVB 2.7. So make sure you update your TVB afterwards. And on the longer term, there are different initiatives under work, like higher resolution simulations and acceleration backends for the simulation, and different extensions to work with external atlases, and so on. That was it from my side.